The organization and development of the land areas within a nursery should be carefully planned prior to development. The best soil types and most level sites should be reserved for plant production. Each unit should be located and developed to produce optimum growth of plants and to maintain their quality following harvest, but still permit efficient use of labor in each phase of the production, maintenance, and marketing effort. The time spent in carefully planning the layout and development of the nursery site is well worth the effort and the efficiency that can be gained in the use of the other factors of production. I'm Dr. DeBosk, and this video discusses the development of the nursery site, including the addition of certain aspects of the nursery that make it more cost-effective, and production programming to ensure that enough plants are produced. The design of container production areas is strongly influenced by a number of factors, including irrigation and drainage, materials handling, cultural and maintenance requirements of the plants, size of the containers, and the costs involved. Drainage is the companion factor to irrigation and must be considered in the development of the container area because large volumes of water are applied to the plants throughout the growing season, and much of this water falls outside the container and drains through them. Excess water is frequently allowed to drain into a sealed pond used for irrigation of nursery stock to reduce the potential for groundwater contamination and to reduce the need for additional well water. The runoff water may be high in soluble salts or spores of various fungi and may need to be checked periodically and treated appropriately or blended with well water. Where the soil type permits, French drains can be constructed to carry away drainage water. French drains are simply deep holes or trenches dug through low porosity topsoils into high porosity subsoils. The trenches are then filled with rocks or crushed gravel. These drains allow the excess water to percolate into the soil where it will be filtered and will recharge the underground water supply. The efficiency of handling materials is probably the most significant factor in the development of the area. Plans need to be developed and the area designed to expedite the efficient handling of materials through the various phases of production, including media preparation, potting, setting out of containers, pickup of containers for shipping, rearrangement for overwintering where necessary, and loading for shipping. A well-planned design should provide for a logical rotation of crops through the production cycle so that handling of the containers is kept to a minimum. The design of the area must also provide for the space needs of machines, especially transport equipment, used in the operation of the nursery. The cultural maintenance requirements also influence the design of the container area. Plants that have special requirements are best grown together in areas where their special needs can be met most efficiently. The size of containers is another parameter that affects the overall design of the container area. Containers are best grouped by size to aid in appropriate irrigation, ease of handling, and maintenance. The blowover of container-grown plants is a serious problem in container production and windy production areas. Most container-grown plants blow over due to lack of stability resulting from the use of lightweight growing medium and the size of the plants. The most commonly used technique to minimize blowover is to mass small-sized plants pot to pot within the growing area. However, as the plants grow and need to be spaced apart, the chances for blowover are increased. One or more of the following techniques can be used to stabilize the plants and to minimize blowover. A wire frame 4 foot wide composed of 6 by 6 inch openings is stretched over the container bed at a height of approximately 4 to 6 inches, secured, and plant containers are placed into the openings. For growers who have sites with well-drained soil, there is an option to use the pot-and-pot system, which prevents blowover. Another technique is to use the wire trellis and plant saddles. In this system, plants are attached to the trellis using the saddles. A new method of producing plants, especially trees in nurseries, is a combination of field-grown and container-grown systems. This system utilizes grow bags for in-the-ground field production phase, followed by production of containers during the last phase of production, just prior to sale. In this system, young container-grown trees, whips, are planted into grow bags and grown under standard field production methods for a year or two depending upon the species and the size of the grow bags. When this phase is completed, the plants are dug, especially in the spring, and the grow bags are removed. The trees are potted into containers of appropriate size and grown in container production for the second phase of production. Many of the trees are sold in the fall of that season and some in the following spring. This production system prevents the development of circling roots in long-term container production and provides a containerized tree, which is easier to successfully ship and transplant than a grow bag grown tree. It is extremely difficult to efficiently produce a wide range of plant material. In order to gain a greater degree of management control over production, it may be desirable to specialize either by type of plant or by method of production. Limiting production to plant groups that have similar production requirements and are compatible with production capabilities is one means of gaining production efficiency. Also, with increased mechanization of routine production operations, there is greater need for standardization of techniques. Specialization and standardization permit managers to plan and control production, thus ensuring a greater chance of success in the business. Production programming must begin with a market analysis to determine if there is a market for the product, the potential demand, in what size and form, and how many plants per year would meet the sales goal. Information must be obtained on production requirements related to propagation, soil and water requirements, general culture in the nursery, and potential pest problems. An estimate must be made of the resources that will be needed, the production efficiency or mortality that can be expected, and the costs involved. Once a production quota has been established for the end product, it becomes necessary to calculate the quantity of cuttings to be stuck, grafts to be made, or seeds to be sown in order to produce the transplants needed. The number of liners that will either be field planted or planted in containers needs to be calculated in order to meet production quotas. In each step of the operation, there is a mortality that can be expected, plus a loss of material at grade out for some classes of plant material and a factor for replacements. These data may be available from past records, or an estimate can be made based on information obtained from other sources. Estimates for subsystem quotas are obtained by working backwards from the estimated production or sales figure. The calculation is made for each step in the production cycle by dividing the production quota of that phase of production by its estimated return percentage. For example, if the production goal is 10,000, 10,000 represents 100%. If replacements are 5%, 10,530 plants must be produced to meet sales plus replacements. 10,000 divided by 0.95 equals 10,530. Space requirements can be estimated for propagation, liner production, and either field or container production. When a continuous production system is designed, it is necessary to know the rotation system that will be employed in addition to the planting densities that will be used in the field or container production areas, the liner area, and the propagation bench. This information can then be used in planning for and adjusting the space needs for the total operation. After the individual species to be propagated have been classified by method of propagation and a priority index assigned, the space and time requirements can be estimated and adjusted to fit the limitations imposed by the available bench space. In the example here, Group D has priority 1 and is plotted first, followed by Groups A and C. Group C must be delayed by 5 weeks due to space limitations, but Group A is programmed according to schedule. Group B, with priority 3, is split into 2 groups, B1 stuck on time and B2 delayed until week 5. Cuttings can be held in storage until space is available. Land use in the production of field-grown stock is generally planted for several years. In addition, the land may be out of production, either lying fallow or in a cover crop for a period of time that will vary from a few months to a number of years prior to replanting. One saleable acre of nursery crops will require a number of non-saleable acres to support the production program. The table on the slide lists estimated acreage requirements for selected classes of field-grown nursery stock. Management practices will vary with type of nursery and production objective. Therefore, the estimated acreage requirements should be used only as a guide where individual data are not available. Land will also be required for turnaround and service road areas and must be added to the above calculations. It is estimated that these requirements may vary between 5 and 10% of the production requirement. Land for the production of container-grown crops is occupied for only a few months for crops with a rapid production cycle, up to 1 to 2 years for species with longer production cycles. Container production land can be used for a subsequent crop almost immediately after a crop has been harvested. This is one of the advantages for container production, shorter rotation time and leading to faster turnover of invested capital. If the market objective is to produce small plants in small containers on a rapid rotation, 1 acre of land may produce 2 to 3 crops per year, so that only 0.5 or 0.33 acres of space is required per acre of annual sales. However, for large plants on a 2-year rotation, it may take as much as 2 acres of land or as little as 1.5 acres per acre of annual sale. Climate and various cultural operations will influence growth rates, which will affect turnover rates. Nurseries located in southern latitudes have longer growing seasons and are capable of producing crops in a shorter period than nurseries located in northern climates. Also, plants that are produced under optimum cultural conditions of light, nutrition, moisture, and pest management can be produced on a shorter production cycle, which will require the time that each container-grown plant occupies space in the nursery. Finally, the required space will be influenced by the spatial arrangement of the containers through the production cycle. In conclusion, hopefully you learned how to reduce costs and improve efficiency and how land is utilized for both field and container-grown plants.